Hello, this is Louis Pritchett, and today I'm going to explain to you how to wire a 4-bit comparator circuit. In addition, I will explain to you how it works, and then I will show you an actual circuit that has been wired. A comparator is a circuit that compares two binary numbers and indicates which one is larger, smaller, or equal. This is a functional logical diagram of a 4-bit comparator which can compare two sets of binary numbers numbering from 0 to 15 in decimal equivalent. These are the A inputs. These are the B inputs. These are inputs from a least significant chip, and these are outputs to a more significant chip. This is the pin diagram for the 7485 comparator chip. Thus, this is what is needed to wire the comparator circuit on a breadboard or trainer. Each pin has a specific assignment: input, output, power source, or ground, and it's fairly easy to read. Bn, for instance, A less than Bn, for instance, meaning that it is a input coming from a least significant chip, to an A0 meaning that it's one of the inputs for the A set of binary numbers. It's very easy to read. This is the pin diagram with the wire locations. To wire it correctly, you first have to place the chip on the breadboard in this orientation. Then the next thing is to connect the ground pins. In this case, pins 2, 4, and 8 have been connected to ground. Next, connect pins 3 and 16 to a positive 5 volt power source. In this case, red wires were used, and to connect to the ground, green wires were used. Then, after determining the most significant bit for both sets of numbers, the A set and the B set, you would then run a wire from the input pin, the input meaning A3, A2, A1, A0, or B3, B2, B1, or B0. Those are your inputs for the numbers that you're going to compare. You would run a wire from each pin to the corresponding switch. In this example, A3 is the most significant bit for the first set of binary numbers, followed by A2, A1, and A0. And they are connected to switches 7, S7, S6, S5, and S4 respectively. And blue wiring, as you can tell, was used. B3 is the most significant bit of the second set of binary numbers, followed by B2, B1, and B0. These inputs are connected to switches S3, S2, S1, and S0 respectively, and white wiring was used. Finally, the outputs. A is greater than B out, A equals B out, and A is less than B out are connected to the logic indicators B7, B6, and B5 respectively, and black wiring was used. Note, I use a color scheme for my wiring, to avoid confusion and to aid in troubleshooting. Since this chip is not cascaded, pins 2 and 4 were grounded and pin 3 was connected to a 5-volt source. I mentioned this to avoid confusion. In the event of cascading, the outputs from the least significant chip will be fed into the inputs of the most significant chip. And again, the inputs for the least significant chip for the comparators will be coming from a lesser significant chip. Or in the case of the 4-bit comparator, these outputs will be grounded and connected to a 5-volt source. Now the way the circuit works is as follows. A function diagram is prepared, and values will be entered for the A set of numbers and the B set of numbers. We're comparing the A numbers with the B numbers. We start with the most significant bit and we work our way to the right, both for A sets and B sets. And then over on the left, we have an approximate, we have calculated what the outputs should look like. Any place there's a 1 on the output would indicate whether or not it was less than, equal to, or greater than B output. For example, in order to compare the A and B sets of numbers, you would input the values for the A numbers, A3 through A0, with A3 being the most significant bit here. And the way you would do that is you would turn the corresponding switches to each pin on or off.
Less than 2 minutes.
Okay, an off pin would be indicated by a green light, and that would mean would indicate a value of 0. And on pin would have a red light, and that would indicate a value of 1. Once you turn the switches to the appropriate settings, then the outputs would go to the indicators. The outputs being A equals B, A is less than B, and A is greater than B, would go to the appropriate indicators. And based on what the actual comparison is, whether it's a 1 or 0, would determine whether or not that comparative condition existed.
1 minute.
Okay, for instance, if A equals 1, then for B equals A, if A equals B, and it was a 1 here, that would mean that if 1 was in either one of these columns, that would mean that A equals B. For instance, in this case, we were comparing the number 9 binary to the number 9 binary, and it showed up as 1 in A equals B column. Finally, here is an actual circuit that was wired up. And as you can tell, the A inputs use blue wiring, B inputs use white wiring, the ground use green wiring, and the power inputs use red wiring, and the outputs use black wiring, the outputs to the logic indicators.